Yeah, 10 minutes for question. If you can leave 10
minutes
minutes for question. Yeah.
Okay. Yeah.
Thank
okay.
you.
This slide was discussed, but where do we? Where do you want
Yeah, we
me
were
to
on this
include?
slide. Yeah.
Okay. So this is a two-block cases. So we have general. This is the RGCCA, which is a general formulation, and in the two-block situation, it reduced to this kind of. You see that the sum is disappeared, and the constant is the same, but G is equal to 1 or 2. Okay. And so if tau J equal to 1, tau 1 equal to 1, and tau 2 equal to 1, this optimization problem reduces to the covariance criterion, and this is exactly PLS regression. Okay, PLS regression, PLS2, maximize the covariance between block components. Is tau 1 equal to 0 and tau 2 is equal to 0, then the constraint is equal is the variance of the component is equal to 1, and variance and you recover correlation. And maximizing the correlation is exactly the canonical correlation analysis criterion. So you see that RGCCA includes a special case, PLS regression, and CCA, which is CCA. And for redundancy analysis, you see that tau 1 is equal to 1 and tau 2 is equal to 0. And you see that there is an asymmetric criterion. And this criterion, you see that the variance of the block component associated with X1 is present in the criterion, but the variance of the component associated with X2 is not present. So you want a stable block component for X1. You want the component for X1 correlated to the component associated with X2. There was no stability condition for the second component. Okay, so this is an asymmetric problem, which can be useful in when you have specific data. This is called redundancy analysis, or also reduced rank regression. Okay, this is a optimization problem associated with reduced rank regression. Okay. And so you have to. So you see that this is important to choose properly the value of the regular of the tau J, and you see that when tau J is equal to when tau J is close to 1, then you're favoring stability of the model, and when tau G is close to 0, then you're favoring correlation. Okay, and when tau G is between 0 and 1, then you have something between correlation and stability, and this is say a regularized version of canonical correlation analysis. And tau J is in fact a regularization parameter, like in ridge regression. Okay. And
is it just possible you put your slide in presentation mode again?
Yes, like this.
Yeah, perfect. Okay.
And in terms, so it's a bit maybe the goal is to have a very efficient algorithm to solve this optimization problem. And so I don't want to go into the detail of the algorithm, just to say that it is an iterative algorithm with a very good properties. We have a monotone convergence of the algorithm, and we have also that it is a global convergence algorithm. That means at the end, at convergence, it's an iterative algorithm, and at convergence, we guaranteed mathematically that the solution we have is a stationary point of the optimization problem. Okay, so it's not the minimum, but it's okay. The two conditions, the two properties we have for the algorithm we propose. And maybe I can switch to application on R. So we can use for the Russett dataset, we can use the RGCCA package. So all the material is present on the drive. So I send the slide and also the notebook and the data. So everything can be reproduced. So we have to load the RGCCA package like this. So library RGCCA. And if you don't have the package, you have to do like this.
Arthur, I think you are presenting the PowerPoint, but the rest of the screen, at least I cannot see it.
Okay, so I have to switch from PowerPoint to R. Okay, maybe now this one. Okay. Now you can see the studio.
No, it's fine. Yeah, thank you.
Okay, so we have a notebook like this. So the first step is to load the RGCA package. Okay. Or if you don't have this, you have to download it. Okay. And then within the package, we have the Russett dataset. Okay. I can show you data. Okay. And you can see Argentina, Austria, Belgium, etc. And all the variables that we discussed in the presentation. Gini, farm, rent for the first block, BNPR, Elabo for the second block, etc. for the third block. Okay. And the first goal is to define the block. So you can see X1 is my first block. I can take the three first variable of the first block. So you can see here X1, X2, which is related to Elabo, and X3, which is related to the last variable. Okay, so I define the three blocks, and we can store all these blocks in a list. Okay, like this. So okay, L is a list which contains X1, X2, and X3. And okay, we can just see the first element of the block is Gini, farm, and rent. The list is Gini, farm, and rent. The second one is NPR Labo, and the third one is the last variable. Okay, and the second step of the analysis is to construct the design matrix, the connection between blocks. And you can see here, we construct the design matrix, so the CGK, which is equal to 0 or 1 if the blocks are connected or not. So X1 is connected to X3, so I put a 1. X2 is connected to X3, so I put a 1. And X3 is connected to X1 and X2 because it's symmetric, so I put 1 here. Okay, we have a design matrix. So we need to define this design matrix according to the experts. And the last one is to design to set the regularization parameters. So TO1 is here for the example. We set TO1 equal to 1, TO2 equal to 1, and TO3 equal to 1. Okay, and you see TO equal to 1, 1, 1. And you call the RGCA function of the RGCA package. You put the list. As argument, you put the list. You put the connection between blocks. You put the TO parameter, etc. You put also the function g of x equal square of x here, and you run your analysis. And you can see here the convergence of the algorithm. So it's a very fast convergence. You see that in a 3 or 4 iteration, you converge to the solution very fastly, and then you can visualize the result. So you have here the weight associated with Gini, the weight associated with farm, the weight associated with rent. So the weight associated with the first block. This is the weight associated with the variable of the second block, and this is the weight associated with the variable of the third block. Okay, and you can see also here. This is the weight. So the weights. So the latent factor associated to agriculture inequality is defined like this. Tile 65. Okay, I can show you maybe the presentation. You can see here the weights. Okay, we can see the PowerPoint now. No.
Yes.
Yes, and this is the weight, the estimated weight. So Gini, the weight associated with Gini is 0.66. The weight associated with farm is 0.74, etc. Okay, and the next step is to say, I have one additional slide. Is this weight are significant? Are this weight significant? Does this variable contribute significantly to the construction of the latent factor agriculture inequality? And so you can do a bootstrap procedure to assess the significance of the weight. For instance, this one, the weight associated with rent, maybe it's not significant. You see that it's very low, 0.1, so it's very low weight associated with rent. We can ask if this value is significant or not. Okay, so you can perform bootstrap. You can do it like this. We have a specific function here, RGCA bootstrap. We take as input the RGCA object. You can see here the name of the object. You take this object as input of the function, and you run 500 bootstrap sample. Okay. So you do the same time, and you can visualize here. So you can assess statistics for the different rates. So you have estimates, you have a confidence interval, lower bound, upper bound. What you have also is a p-value, a bootstrap ratio, the adjusted p-value with a FDR correction or buffer-only correction. So you can assess the significance. And also what you can do is visualize the bootstrap confidence interval, like this one. Okay, and you have a visualization of the weight, the initial weight, and the bootstrap confidence interval. And you can see that trends across the zero value. You can see that you have the zero value here. You have the weight associated with rent, the bootstrap confidence interval associated with rent across the zero value. And so we can conclude that the weight associated with rent is not significantly different from zero, because zero is included in the bootstrap confidence interval. Okay, you can see the same for you can see GMPR and Labo, which is significant. You can see that INST is not significant because the bootstrap confidence interval cross zero, etc. And then you can see, as usual, as in PCA, you can see the factorial plan, where in the x-axis you have the component, the first component associated to agriculture inequality, the block agriculture inequality. And in the y-axis, you have the block component, the first component associated to industrial development. And you can locate the countries in this plan. Okay, and if I go to conclude the slide, you can see here that on the top you have countries with democracy stable. And okay, I can comment on that also. Oh, sorry. I have to do that. It's important. You can see that agriculture inequality is positively correlated to political instability, which is quite logical. When you have high agriculture inequality, then it tends to have high political instability. When you have high industrial development, so high industrial development, then it tends to be negatively correlated to political instability, which is quite logical. And then you can interpret the correlation between the concept, between the latent variable, but you can also interpret the contribution of the original variable to the construction of the latent factors. Okay? And you can see that Gini and Farb contribute significantly to the construction of the latent variable, but rent does not contribute significantly, according to the bootstrap confidence interval, does not contribute significantly to the construction of the agriculture inequality. And the same and we have the same interpretation for all the block. Okay. And to conclude this part, you can see that you can plot the first component of the first block in the x-axis, and the first component of the second block is the y-axis. And you can see here the stable democracy on the top. On the below here in grid, you can have the dictatorship, and in the middle you have unstable democracy. Okay, and what you can see France here, which is labeled by Russett, which was labeled by Russett as unstable democracy because it was at the end of after the independence of Algeria, and you have the executive was very unstable. So Russett thought that it was an unstable democracy, but his economical factor tend to think that it will be good for France and will be a stable democracy. And in opposite, you can see Argentina, Chile, Greece, Brazil, which is located around the dictatorship in 1964. And some years after 1964, you can see that there is an important event in Greece with the dictatorship of the Greek colonel, in Chile with the dictatorship of Pinochet, Argentina with the military dictatorship, Brazil with Branco. So a few years after 64, they known a period of dictatorship. So it's quite interesting to see that it is quite interpretable. So I think I have to stop now, but just want to, so it's a very small example, but you can use it in a high dimensional context. So this is an example here when I use the sparse version of RGCCA in a very high dimensional context. You can see that we have 53 observations characterized by 3 blocks. The first block contains more than 15,000 variables. The second block contains more than 1,000 variables. So you can use this method also in a very high dimensional context. But if you want to ease interpretation, you need to add sparsity parameter, and you can do that by changing the constraints, by adding a lasso constraint in the optimization problem. Okay, and adding lasso constraint in the optimization problem provide variable selection at the end, and you can interpret which variable contribute to the construction of the block components, and which does. And so there is only few variables that contribute to the construction of the factors. Okay, so maybe I can stop here. You have the slide, you have the code, so you can reproduce all the results, and maybe if you have questions, I can try to ask to your questions.
Thank you very much, Arthur, for this brilliant talk. I think you did a wonderful job summarizing the theory behind the different dimensionality reduction approaches. Is not an easy task to explain that soft differences in the objective functions and optimization problems, and you did it in an excellent way. And
thank you.
It's also really good to have this package, RGCCA. We have used it personally in a project in Helix that will be presented in the next session as a case study, and it's an extremely powerful tool with different implementations for obtaining inferences, as he said, performing as well the feature selection, so it's able to deal with high-dimensional data sets. Also, the nice contribution plots with the weights, with the bootstrap is really nice. So I recommend its use. And maybe people, if you want, you can use the chat for having your questions. Well, we have some questions here in the chat. Let me.
Should you manually insert which variable belong to each block? So yes. So the idea is to manually insert which variable. Yes. So at the beginning of the analysis, you need to define which block. So as you can see in the notebook, at the very beginning of the analysis, we need to define which variable are present in each block. Okay, you can see here that where is it? It's here. At the very beginning, you say which variable is present for each block in each block. So you need to manually insert. So yes, the question is yes. You need to define the block at the beginning of the analysis. Yes, okay. So yes, so it's usually you see that you have a set of blocks, and the blocks are known a priori. Okay, but sometimes you want to define by yourself the blocks, and for instance, if you are in a genomic context, you have you know that some genes belong to some pathway, functional pathway, and maybe you can do, instead of considering a big block of gene, what you can do is to say maybe some genes are correlated together because they are belonging to the same pathway, and so I want to create a block for per pathway. So it's possible to do that. If you have an idea of how you want to define your block, you can do what you want. The idea is to say, okay, I have an idea of what I want to do with my data. I want to do it by pathway, for instance, and so I have to create my block according to the idea I have at the beginning. Okay, so it's possible to do what you want. I'm not sure I have answered the question, but you need to define the block at the beginning. And if you have an idea of how you want to define the block, then you can use it.
Yeah, I think there is another question from Tanya asking if there is an imbalance between the different data layers. For example, we have 20,000 genes in the gene expression layer and only 1,000 sites in the other. If this will need to be addressed in some way.
It's a very important question. I didn't discuss that in the presentation, but yes, the method is very sensitive to the dimension of each block. If you have a big block and a small block, then the big block will take all the will weight more in the analysis. So you need to pre-process the data. So this is done in the RGCCA package. So you need to kind of pre-processing, which try to balance to equilibrate the contribution of the block in the analysis. So we have different strategy implemented in the package. One are proposed by default, but you have different strategy to weight the block when we have different.
If I can,
yes.
If I can add at the next session, that in the case study we will mention that because we had the problem with Ines now that there was methylation data, very high dimensional, and protein data with only a few variables, and I think she will give an example on how to deal with this.
Okay. So just to show, yes, just to show, you can see here scale. You can see an argument here, scale block, which is equal to inertia by default. But you have a different option that enable to equilibrate the weight, the importance of the block in the analysis. Okay, and this is the well-known pre-processing of the literature. From an analytic chemistry perspective, different omic technology are suited with different measurement uncertainties. Even within a single omic measurement, uncertainty might differ and are often not tracked or different systematically. This means that the noisiness of the individual blocks and or the variable with the single block different but typical in them. It's a very long question. Wait a minute. From an analytic chemistry perspective, different omics technology are associated with different measurement uncertainties. Okay. Even within a single omic dataset, measurement uncertainty might differ. Right. That the noisiness of the individual block. Right. How would you account for this during the configuration? It's a good question. Would this be the case for optimizing weights by bootstrapping? It's clear that if we are doing bootstrap and if we have a noisy block, probably the bootstrap will tend to not to offer significant bootstrap confidence interval, but yes, but yes, if we have, it's a difficult question because if you have a noisy data set, then whatever you are doing, it's complicated to have interesting data, so interesting results. So maybe what we have to do is to, I don't know, maybe, yeah, I don't have definitive answer. Yes, maybe the data need to be analyzed before and pre-processing is necessary. Yes.
Yeah, there is another question about the.
Does it mean that if we include? Yeah. Yes. So this is Tatiana would ask a question. Yes, and so we include pre-processing pre-processing at the very beginning of the analysis, and this is included in the RGCCA package. So are the estimate for the path mutually adjusted for the other latent factor? Yes. So yes. So for the path, so the correlation between latent factors. It means so it's a two-step procedure. The first step is to estimate the latent factors, and once you have estimated your latent factor, you can compute the correlation. And this is a two-step procedure. Okay. So as the estimation plan. So, but you are estimated the latent factor. You are the weight are estimated jointly, considering all the blocks. So I'm not so.
Yeah.
So the path, I guess, is a correlation.
There is another question about the definition of the shrinkage parameter, the tau.
Yes.
They wonder if it would affect a lot the final results.
Yes. So the tau values definitely affect the results because the optimization function is not which is I would say that is completely related to the tau values. So if you are so for instance, if you put tau equal to 0 for all blocks, you are maximizing the correlation. If you put tau equal to 1, you are maximizing the covariance. So it's not the same objective function you are maximizing. So it's important. And more importantly, if you put tau equal to 0 in a high-dimensional setting, you don't put regularization, and it's not possible, in fact, to use tau equal to 0 when you have more observation, more variables than observation. Okay, because when you have more variables than observation, like in a multiple regression, you need to regularize, and tau plays a role of the regularization in RGCCA. Okay, so that's why we propose different strategy to estimate the tau value automatically. It depends on the context. We propose an optimal technique, an analytical technique based on so based on the fact that we are some place we are estimating a covariance matrix, and tau plays a role of regularization in the estimation of the covariance. So we can use an analytical formula to in the literature to estimate tau automatically, but you can also estimate tau by cross-validation or by permutation. We have two alternatives. If you are in a supervised context, I didn't discuss that here, but you can use RGCCA in a supervised context, and in a supervised context, you can estimate tau by cross-validation. And if you are in an unsupervised context, you can use tau by you can estimate tau by cross-validation by permutation. Sorry. So in the package, you have a lot of functions that can use to estimate tau automatically.
Yeah,
so
that's a really good point. That's a really good point. Just to add something following these questions about tau,
yes.
Sometimes in some omic layers, especially for example in DNA methylation.
Augusto,
important out. If also the definition of tau may affect how the method is sensitive to these outliers, because if I'm not wrong, I think the correlation criterion is more sensitive to outliers observations, maybe, or if we have outliers in one of the layers, should we define tau according to that or not?
I think if you have outlier, it's a kind of problem. But you can the value of the tau value is
Arthur?
Yes, you can hear me. Can you hear me?
Us, Arthur?
Yes, I can. Yes. Yes, can you hear me?
I can hear you both, actually.
Yeah.
Okay.
Yeah, I think we have lost Arthur, maybe?
No, I'm here.
Augusto, you've been cutting. Maybe that's.
Well,
Leah, can you hear me?
Yes. Yeah.
Okay. So if you have an outlier, maybe.
Leah, are you around?
Yes. Yeah. I'm here.
Okay. And so what was? Yeah. So again, if you want to estimate tau, you have a specific function by cross-validation. If you are in a supervised context, it's possible. And if you are in an unsupervised context, then you have kind of RGCA permutation, which allow estimating the tau value automatically also. Okay. And when if you have outliers, then you have outliers, so you maybe have to remove outliers if you can, or you have to do something, but yes, thank you. I'm just interested into fully quantitative data and type of relative quantitative. Yes, maybe we can discuss that after the meeting if you want.
Okay. Well, that was very interesting and very well explained. Agosto, should we close the session now? That's okay. If there are other questions that comes up, maybe we can leave a little bit of time at next session to answer. If people have questions, they can write to Rodney, and
Okay.
and we can.
And you
leave a
can
little
write to
bit
me
of time.
directly if you want.
Ah, yes, if you want to share your email address through the chat.
Yes.
Okay. Great. Well, thank you very much. And the next session, there is a bit of a gap. It's September 25th because of bank holidays and other events. Thank you very much, everyone. Thank you, Arthur and Augusto.
Thank you very much.